Yes, ma'am.
Okay.
Clearly visible.
Okay. So now that we know about the type of QKD, the security principles which are used to strengthen or to ensure that any cryptography which we are using as an application of quantum communication is strengthened by those laws of quantum mechanics. Now we will be looking at one protocol. So before we begin, we will again just have one glimpse of how the architecture looks like. So you have an Alice and a Bob, a transmitter or the receiver. If it is entanglement based, then you have a Charlie, and receiver 1 is Alice and receiver 2 is Bob. Okay, so this is the structure. These two parties are connected with a quantum channel and a classical channel. Okay, so a quantum channel, it can be a free space or it can be fiber. There is a classical channel which can be a IP network. It can be an optical also. So Alice's module will be taking the message, will be taking the encryption algorithm. So QKD is not about encryption algorithm. So you are taking an encryption algorithm, you are generating the keys. That's all about QKD. So you are generating the keys, secure symmetric keys at Alice's and Bob's side simultaneously, spontaneously, in the presence of an eavesdropper. Okay, so this should be clear. Will input will be the message. Alice will have the encryption algorithm, Bob decryption algorithm. Two channels, quantum channel and classical channel. Whenever anybody talks about satellite QKD, free space QKD, it is the quantum channel which they are referring to. That means satellite QKD means that there will be a free space from the ground station to the satellite, and that is the quantum channel they are talking about. If it is fiber QKD, then the Alice and Bob are connected via fiber through which the quantum data transfer is happening. That's why it's called a fiber QKD. Okay, and you see the arrow here, the encryption decryption keys in symmetric, they are same. So it is getting generated at both the sides. It is never transmitted. And the secret coded message, the cryptogram will be sent. Again, to give you an idea, the keys after the QKD is over, there will be symmetric keys stored at Alice's side and the Bob's side in the key management layer or in the key bank. Alice will fetch that key. Alice will tell Bob that it is the third keys which I have used. Okay, the key ID may be shared. So Bob will be referring to that key ID and using that key for decrypting the message. Okay, I hope this will bring clarity on how this entire thing works. Now, we in the earlier session we had discussed about non-orthogonal states, or non-orthogonal states and non-commutation and commutation, right? So here we will be using photons. So polarization of a photon we'll be using to encode information. We will be using rectilinear basis, one set. Let me say one set which is vertically polarized. So quantum mechanically, I will say Ket0 state is vertically polarized for in rectilinear basis, and Ket1 state is horizontally polarized, represented by gray ball in rectilinear basis. Okay, so please be very careful. But when I'm explaining this, in the second part, I am representing 45-degree polarized light using a blue ball represented by Ket plus state in the diagonal basis. And binary, this can be a binary information made. This Ket plus is my 0. Again, Ket minus is represented by 145-degree polarized light represented by a green ball in diagonal basis. Classically, this will be interpreted as binary 1. Okay, so Ket 0 can be binary 0, Ket 1 can be binary 1, Ket plus is binary 0, Ket minus is binary 1. Okay, so now, which means you need to know the basis correctly so that your binary information can be decoded correctly. So the 0 degree and 90 degree are orthogonal states. Inner product of orthogonal states is 0. Then you have 45 degree, 135 degree orthogonal states. But if you take 0 and 45, or 135, 90, 135, so 0 or 45, 0, these are non-orthogonal states. So if I ask a question, whether it is a rectilinear basis or diagonal basis, and I have the right measurement instrument, because a measurement device which measures the horizontal and vertical will not be able to measure diagonal states with certainty. Okay, so there is a different instrument here and a different measurement instrument here. So if I need to ask rectilinear basis or diagonal basis, I need to use the right apparatus to discriminate them with certainty. If it is incorrect apparatus, my states will be disturbed. Okay, and there is no going back. Okay, so the states are disturbed, and I can monitor that so many states are getting disturbed. That means somebody is eavesdropping on the channel. So if this particular page is very clear, because I'll be using BB84 using polarization of photons, and it is a two basis, mutually unbiased basis are used, rectilinear basis and diagonal basis. I will talk in terms of balls: red ball, gray ball, green ball, and blue ball. If I measure a state which was red in color using an instrument which was used to measure diagonal basis, the color of the ball at the outcome changes to green or blue. So looking at green and blue, I can never say that what was the initial state of the system was. So these are those principles. Again, when we say that quantum Xerox machine is not possible, I cannot distinguish the states with certainty, it gives rise to error. So all these play a very important role in quantum cryptography. So here is a mathematical interpretation of the same. So here we have written the measurement operators. Measurement operators for each and every state. If we consider a situation, okay, so you can see the measurement operator 0 is for 0 state, measurement operator 1 is for 1, m plus and m minus ke liye m, yeah, I think this should have been plus and this should have been minus. So m0, m1, m plus, m minus are the measurement operators for or let me be more specific. M0 is for, and M1, M0 is for red, M1 is for gray, M plus is for blue, and M minus is for green. Okay, so from equation 1 and 2, we find that if I'm using these measurement operators, they commute. Mathematically, they commute. That means I can distinguish the states red and gray with certainty. Okay, using M0, M1, and using M plus and M minus, they commute. So I can use these measurement operators to distinguish between green and blue with certainty. But my measurement operators M plus, M0, they do not commute. It's not equal to 0. And hence I cannot use M plus measurement device, measurement operator for finding, for non-orthogonal basis state, 0 or 1. So these four equations, 3, 4, and 5, 6, tells you mathematically that these measurement operators cannot be, these states cannot be measured simultaneously. So again, to take a further dive in that, if you have some quantum magic boxes, so this is a game I usually, present this to the audience when I'm talking about or explaining quantum QKD. A classical box is there and a quantum box is there. So in classical box, whichever sides you open, so different sides are the different measurements you opening, you will always see the same color ball. Okay, the color of the ball was prior decided. Okay, and the color of the ball does not change based on the measurement. Okay, so in the classical world, a yellow ball or a blue ball or any color of the ball, if I'm putting under in a classical box, it remains the same, any measurement I do. But in quantum box, if I'm having a quantum box inside which obeys the laws of quantum mechanics, then based on the measurement, okay, the type of measurement, the color of the ball changes. Again, if I'm having a gray and a red ball, you will see they commute. Okay, they commute. If I'm having a red and a gray ball and I'm using this measurement device, then the output will always be gray. If the input was gray, output will always be red if the input was red. Similarly, I take another two states, orthogonal, green and blue, and I'm using another measurement instrument which can having measurement operators m plus and m minus. So using this, I can always distinguish the state at the output and infer information about the state at the input. Okay, so I'm very certain about it. But if I do not know the state which is coming in, for example, I have jumbled this up. Okay, and instead of m01, I have m plus minus here. Okay, so if the input to the m plus minus box is, say, a red ball, then the ball which comes out of it after measurement, okay, will be either a blue or green in color. So it will no longer be red. So it's a magic. But if the ball is red ball and I opened the side M01, I'm using M01 measurement, I will see the right color. So this is a trick. So the QKD protocol I'm trying to explain is all based on these games. Okay. So the eavesdropper or the hacker or somebody who is tampering the device, he does not know what states has been sent. I'm sending randomly out of these four states. Okay, so the eavesdropper does not know which states. So he will randomly shuffle between these two boxes. In sometimes he will get the right box with the right measurement instrument. The right pair will be there. At that time, I'll get the right output. But other times, I will have a mismatch. M plus minus used to measure red gray, or M01 used to measure green blue. Okay, in those cases I will find errors. Okay, the color of the ball would have changed, and then okay, so at least this part should be clear. Then we move ahead. And we know, of course, that that if there is a mismatch, then the output or the output color of the ball changes based upon the nature of the measurement instrument. If it is plus minus, then these two, red and gray, will become blue green. If it is measurement box was 01, and if it was green, blue green, then it will become gray and red. Okay, so then quantum cryptography comes to a very simple, it's very simple. So if I'm asking the right question or not, asking right question or right measurement, you will get a right answer. If the ball was red and I asked the right question, rectilinear basis or not. Remember, the question one was, it was rectilinear basis or not. Okay, so right state, right question, right answer. Blue state, it is diagonally polarized light. So again, the right state, right question, whether it is diagonal basis me green or blue, you will get the right answer. So it's very simple. But if you do not know about the state and you ask the wrong question, or you do wrong measurement, okay, in that case you will get random answer. It is not pre-decided that if you use a red ball and you use a diagonal basis measurement equipment, you will get green or blue. You will have equal chances of getting green or you will get blue. Okay, so there is no prior information whether the state will collapse in green or blue. You can get this or you can get that. That is the random, and it is supported by mathematics, and you observe this physically when you're doing the experiment. Similarly, if the ball was red, blue in color, and you picked the wrong measurement device, which was supposed to find out red or gray color, the output will be either red or gray, and the decision is random. There is again no prior information that it is going to get collapsed into red or it will get collapsed into gray. That is the randomness we are talking about, but that is again the certainty I'm talking about, that it will never be blue. It will be either this or that, and not any other color as well. So and this information comes from the basis, from the measurement operator. So then quantum cryptography is simple. We say asking right questions or measurement, you will get right answer. Asking wrong questions, you will get random answers. Not wrong answers, but randomly wrong answers. So asking wrong questions, any incorrect measurement damages the original state. It changes the color. So only Alice knows the correct question, and Eve will guess the question and will introduce disturbances. So all these exercise actually helped me talk about or or explain quantum cryptography or a BB84 protocol when I was working in industry, okay, without getting too much of mathematics. But it's and I think similar technique can also be used when you're talking to children and trying to educate them, giving them an intuitive feeling about what quantum cryptography or a BB84 protocol looks like. So now this should be very easy to understand. Okay, so here I'm talking about Alice generating random numbers 0, 1, 0, 1. So somebody had asked a question in the last session that am I distributing the keys or not? So I am generating quantum states. I am randomly encoding them in 0, 1. So let binary 0 can be, you remember the two basis state I spoke about? It can be ket 0, it can be ket plus, okay, depending upon what is the measurement basis. So you select those, generate those random numbers. Then this is here 0 corresponds to binary 0 corresponds to 135 degree polarized light. 1 corresponds to vertically polarized light. Okay, so this is how she's encoding them. Hmm. Vertical 135, 0, 45, 90, like that. And she's doing it randomly with each and every perhaps optical pulse. Or after a certain duration. Then the qubits now which are reaching Bob, now if you make them travel through some particular medium where birefringence, because of birefringence, there will be some distortions. But then you need to correct, and there are ways to correct the polarization as well. But if the state has flipped entirely, then of course it gives rise to errors. Okay, then qubits reaching Bob, you will see some blanks because, as I said, there will be some absorption, some losses. So you will only get a fraction of the data which was sent from Alice, and that fraction is again randomly selected by physics, not by any human intervention. But again, there are ways to hack and tweak where you can do it, where you do it on purpose and introduce some errors, right? And that's a different area altogether. But that is actually it makes sense to explore that as well. Then Bob will be randomly choosing between the measurement equipments, rectilinear or diagonal. It is again randomly generated, these basis measurements, and then he detects them because he's finally converting the information into binary. So he gets a partially binary values data stream. Okay, and then he tells Alice his measurement basis. Then Alice will be, so this is a sifting layer which I have not discussed. Now since you are using two mutually unbiased bases, you need to arrive at one page. So you will actually Bob will tell Alice which measurement basis he has used. And if Alice's bases do not match, you remember the questions, the two questions, if the two questions are same, then measurement instruments are same, okay, encoding and decoding, they will keep the state. Otherwise, they will discard. You see the unhappy smileys. So we will be discarding those states. You will see that Alice has prepared this in a rectilinear basis. This is horizontal, whereas Bob is measured in diagonal basis. So they will drop it. The one which he keeps is Alice vertical, which means rectilinear basis. Bob is measuring in rectilinear basis, and he should be getting the right answer. So he keeps those keys. Okay, so he should be getting the right answers. Now, while processing, okay, the next step is error correction. So Bob will send a stream to Alice, uh, a section, say 25% or 10% fraction of sifted key to Alice. Then Alice will compare her numbers with Bob's number, and then she will estimate the errors, because they should be getting same. But if the error is more than the system threshold error rate, then they will conclude that somebody is eavesdropping the communication, and they will immediately drop it. So this is how the QKD happens. So this entire process is execution of a quantum key distribution protocol. Now there is again one clarity I would like you to attention here. That this all things, when Alice generation, Alice sending quantum data transmission, Bob's detection, comes under quantum data transfer. So when I am saying QKD protocol, a physicist, an experimentalist, okay, would be talking more about the quantum data transfer following a QKD protocol, which is BB84, B92, DPS, cow, whatever. So that is what. But now, if you look at the architecture of QKD protocol, all I did was only this part, and everything below from sifting, which comes from here, is classical. Error correction, error estimation. This is quantum error correction, but not the quantum error correction in quantum computing. So these are all classical error correction based on parity methods to find out the errors in the bits. So from here we do sifting. We select the right basis. We have sifted key. Then we do error estimation by Bob sending a fraction of the data he has got. He will be sending it to Alice. Alice will find the threshold error. If the threshold error is again dependent on the QKD protocol. Okay, so a BB84 has a different threshold, because you have the process of communicating, of arriving at the partial or arriving at a raw key is different in different protocols. Okay, in BB84 there are 4 encodings, B92 there are 2 encodings. Okay, in DPS if there is a phase encoding, BB84 can also be done through phase encoding. So based on that, the thresholds are also different. Threshold depends upon the security, comes from the security of the protocol. We'll come to that later. Then error correction. Now, after doing data communication, I think I missed a very important point earlier, that whenever I'm okay, well, fine, I'll cover that in during eavesdropping. Okay, fine. So this is the error correction, and after that they do analysis. Okay, in analysis they consider how much of the key has been or parity information has been leaked, or how much um, information has gone because of the nature of the photon source, because of the intensity or the performance of the QKD system, because of the nature of the QKD protocol. All that is analyzed. The leakage, possible leakages are identified, and then we do privacy amplification, we do hashing, and after that we are able to fetch out the secret communication. Okay, so now this all we have covered these principles in the last session. So quantum, the photon we are using, you know the principles behind it, you know how we are encoding, particularly through the polarization example, why it is secure, basically through the physics supporting, physics coming to the rescue and giving you indications that somebody has perturbed the state. And then we do one QKD protocol. This is entirely, the first part is entirely the quantum data transfer. And whenever you are seeing the message that Bob tells Alice, how he will tell using the classical channel. So earlier I had shown you those, that QKD picture, no, Alice and Bob. So then there was a classical communication between Alice and Bob. So Bob is telling Alice using classical channel, not the quantum channel. So he will do all the communications. So in that communication only, so the communication starts happening from sifting, error correction, error estimation, error correction analysis, privacy amplification, and finally secret communication. You will also see emergence of the word key after the quantum data transfer. And I think I have clarified that point, that we are not sending the key, we are generating the key at the both the ends simultaneously. And here, one more thing I wanted to talk about is, we only use photons. We may use different degrees of photons. Then another thing was security requirements. Now, the security framework of each and every QKD protocol is different. There is no standard one security, for which is applicable to prepare and measure error corrected and entanglement based QKD protocols. And that is derived using lot of maths, since in quantum physics we can get a mathematical formulation of the physics which is happening. The investigation is very deep, okay, and it is very difficult to establish the security of a protocol. So it is preferred that we stick to the fundamental QKD protocols, and thereafter, based on the market requirement or user requirement, we customize it. I would not say even tweak, but rather customize it. Okay, so one slide I was looking for is, I would like to talk about this first. Okay, so after completing the quantum data transfer, we have seen that we have actually worked only with the photonic qubit. Photonic qubit is known as the flying qubits. And as you can see that so why am I actually discussing this slide? Because when I said that it is this entire field is in multidisciplinary, you need experimentalist, but the experimentalist needs to have an idea of the quantum information also. And to explain that, I have included this slide and the next one. So we begin by saying that a qubit is a two-dimensional quantum system, which means that its Hilbert space is spanned by two basis states. The two basis states, the two orthogonal states, okay, and we have represented here as ket0 and ket1. These are also known as computational basis states. Computational basis ket0, ket1, diagonal basis ket plus, ket minus. And in fact, all the states of the qubit can be expressed in computational basis with this equation. Now, this equation is very important, and you can see the angle and phi here. They are two independent degrees of freedom, and through this we can point anywhere in the sphere. Okay. Now, so now we know that the qubit, it's a quantum entity, and it will follow the unitaries, because any evolution is a unitary transformation, right? So we have to keep that in mind whenever we are doing the quantum encodings and quantum measurement. The quantum measurement will follow the laws of or the postulates of quantum measurement. You have to refer to the postulates. Quantum state preparation, you have to follow to the quantum postulate of state generation. Okay, so you have to adhere to those postulates when you design or when you start implementing experimentally a QKD protocol. Now, here I have just shown 3, but there are actually more than 3. One is the spatial mode. So these are known as state preparation. And in this, I think I've also referred to the thesis where if a good description of this matter is there, and it talks about primarily differential phase shift QKD, but it has very good introductory chapters. Okay. So here it talks about spatial mode. In spatial mode, what you do is a single photon in mode 1 is separated spatially into two modes, 2 and 3, using a beam splitter, okay, and a phase shifter. Okay, so you can represent this as in this equation, and you will see that ket 0 and ket 1 is assigned based on the presence of the photon in one of the two modes. Okay, if it is in second mode, then I'm saying it gets 0. If it is in third mode, then I'm saying is it is in ket 1. So this is how I am classifying them. Then we have polarization. Polarization I have already discussed so much. So you can take a horizontal, vertical. You can take right circular, left circular. You can take 45-degree and 135-degree diagonal polarized states. Okay. Then we have time bin encoding. Okay, in time bin encoding, here as you can see that you are actually sending um, uh, you know the state using a delayed interferometer. Okay, so you have a shorter path and you have a longer path. Okay, so when one photon comes out of it, you have one pulse, a wave packet comes out of it. It is now you can see them now into uh, two modes, two time slots, T1 and T2, using this asymmetric interferometer. And then you're also modulating the phase in the longer path. So yes, practical QKD schemes are also derived using time bin encoding. Now, if suppose I have to do a free space, I will be preferring polarization. If I'm supposed to do a fiber, I will be preferring a phase encoding. Time bin encoding is also useful here. Here, as you can see, that the information is encoded in the relative phase of these two time slots, and here it forms a basis of DPS QKD. Or differential phase shift QKDs are based on these kind of phase encoded delayed using asymmetric interferometer. So this encoding principle, and there are still ways. It's still people are thinking on how to encode information on the photon using orbital angular momentum and using different encoding techniques. Okay, so that is what I wanted to bring out. So after the data transfer, we are going to error correction. Now, why do I say that error correction is needed? I had mentioned that we are dealing with non-ideal non-ideal equipments, electronics, and so a bit may flip if somebody is more accustomed to a casket. Then the noise models, there are different noise models, but when you do it practically, you're actually either flipping the state. Okay, most of the time it is a bit because of any of the reasons. It's actually flipping of the bit, depolarization or dephasing. So it's interesting on how to map the quantum noise models on a realistic QKD. That's very interesting. But however, let me bring your attention to the Shannon's noiseless coding theorem, which tells us that the minimum number of bits, say k, that is publicly exchanged to collect the errors e. So there is a bound here, and n is the length of the raw key. And here we have considered the shifting parameter as 1. Now, now usually, so there is no particular error correction algorithm. Okay. But it's again something, we look at LDPC codes, or we look at cascade error correction schemes to kind of which can come closer to the Shannon's limit. Okay, and then again we try to do the error correction using unidirectional or bidirectional. So we have to look into the resource, and because the longer we do, the more information also we are giving to the eavesdropper, who is an active listener of the classical channel and a very smart tweaker for the quantum channel. Okay, so what I mean to say is that it will not, what we assume is that he will not be or we are not bothered if he tampers with the classical, because that's not the problem. We are only solving the quantum channel, the data line, the quantum transfer line, so that if any eavesdropper is trying to hack, we should be able to find it. So using this error correction algorithm, we'll be trying to arrive at a correlated binary bit stream at both the ends. And after having done that, after getting the error corrected key, we will be looking at the privacy amplification. So privacy is the secrecy. So you need to study the generalized privacy amplification theory here. The main idea is to reduce the shrinking factor. So shrinking factor tau, by which the error corrected key has to be compressed. And how much is the compression? It depends upon the error rate. And so we ensure, so what we do is that we ensure that the Eve's information about the final secret key is lower than a specified value. And that is what we take care of. And when I had said that we shrink, the final secure key is way lesser. If I'm sending some millions of qubits, then I'm getting some thousands, and then again I'm further getting reduced because of error correction. I'm sending 25%, and again I'm reducing it because I'm doing hashing to ensure the secrecy. So in this way, my the length of the QKD keys is also reducing. Okay, and I have to ensure that the secret key is compatible or is healthy to be used for any other cryptographic application. So that calls for more stringent bounds, and that decreases the key length per second. Okay, so now I hope you got an idea of what are the concerns, but at the same time, if the engineering is done in a very smart manner, today the QKD errors can be reduced to as much as 1.5%. Okay, in that case, my length of the secret key is also reasonable enough. But at the same time, it is. Let me give you an example that whenever we are doing any secret communication, classical communication, we are doing in gigabits, right? But the key generation rate here using quantum key distribution is of the order of megabits in some, kilobits in most of them. Okay, using satellite QKD, it is way lesser. It is some 1,000 bits in a year. Okay, because you have to actually be in sync with that small time window. You do not also have ground stations everywhere, so there's a lot of challenges there, but there is absolutely no doubt on the security which quantum key distribution brings in. Theoretically it is there, but it has to be implemented in a secure fashion, and therefore it is prescribed for very high security network. Okay, and we believe that it is the post quantum cryptography and the quantum key distribution coming together to address the problem of quantum secure communication. So now with that, let me come to the final section of our discussion today, which is on quantum adversary. So it is basically a part of the first session, because we wanted to talk about security. But now, since you are having the idea about the entire quantum key distribution steps and processes, you understand that where all the hacks, or it can be the loopholes, are there, and how it has, and the need to address it. So before starting this again, I would say that there has to be a clear understanding that we're talking about Alice and Bob with a quantum channel and a classical channel. There is an authentication to begin with, where Alice is authenticating Bob, vice versa. But again, it is not part of a QKD. It is a part of the product which has to do so, right? And there are algorithms in the classical framework, which gives information theoretic security for authentication, for hashing. So I'm not solving that problem. My problem, the problem which I'm solving using quantum communication, is the quantum data transfer. So the quantum adversary, who has the power of physics, quantum physics, not only classical but quantum physics, can tamper with the quantum channel. So the quantum channel is what I will be looking at. So we classify them, or we categorize them into three categories. Okay, and based on these attack categories, we define the quantum attacks. One good example is the photon number splitting attack. So I know that if there's a high probability that I will be sending only one photon if I'm attenuating a laser, but there are a chance, finite probability, that there will be more than one photon. So I know that so the quantum adversary will be able to devise a weapon such that if there is a two photon, he can pluck out using optical tweezer one of the photons and derive the information from that. Okay, so those are the possibilities we give it to the quantum adversary. And when we formulate this quantum security, we consider all such possible attacks by the quantum adversary. We take them into account and we put that in the equation of privacy amplification. Okay. So then the attacks, we classify them into three categories. One is the individual attack, and the other is the collective attack, and the most powerful one is the coherent attack. Okay. So if for perhaps for standardizing a QKD protocol, if there is a protocol which can be cleared against coherent attack, then that gives a strong chance, which of course BB84 single photon is, for standardizing a QKD protocol. Okay, so now let us talk about the individual attack, incoherent attack, or the individual attack. So here the Eve is restricted to entangling a quantum probe to each qubit separately, independently, and you will see that he measures them independently. Okay, and then you may or may not have a quantum memory. Okay, so again, one of the important things is I'm giving the adversary the power of quantum memory and quantum computer also. So when I'm doing the security calculations now, I'm also considering the possibility of a quantum computer and a quantum memory. Okay, so in the first level of attack, I'm not, I don't need a quantum computer, or I don't need a quantum memory. Alice and Bob are doing some classical communication. Remember, I had mentioned this in the earlier slides also. So based on that classical communication, for which Aleph is an active listener. Okay, so he will use that information to select the measurement basis when he is working on his his states. Okay, and based on that information, he will get more information. If he doesn't listen to the to the conversation between Alice and Bob, his chances of getting more accurate results are lesser. Okay, and such attacks comes, you can put the following attacks under this category: incoherent attack, which is intercept and resent attack, beam splitter attack, photon number splitter attack, and general individual attacks. So some of these attacks, like the IR attacks, have been demonstrated for some QKD protocols, and some software simulation of beam splitter attack has also been published. Okay, so this is one of the attack which is very realistic and which is very nearer to the classical with the present technology, and they can be performed. So here is a list of such attacks. Denial of service attack, some other active attacks is also possible. So these kind of attacks are very actively investigated, and most of them are focused around the detector and the source. The detector is in fact is the Achilles heel, and one of the reasons we use to attack either detector or the source is because they are connected through this quantum channel. I can use different loopholes in implementation design by deliberately designing such equipments or selling such equipments to the user, such that they induce biasness, okay, and attacks can be possible. So this is just a few of them, and you can see that mostly the papers are around 2019. The latest one is in 2019, but a lot of other a lot of work has been done after that in present times, and they are more on realistic implementation, or they are more on simulated attack. Okay, it's a very good study case. The second, we come to collective attack. Here, the Eve can entangle her system just similar to the individual attack. Similarly, she's entangling her system. Eve is entangling her system, and she can perform a global measurement. And in this attack, she needs a quantum memory, and she needs a quantum computer also. So what she does is she can perform a special quantum measurement known as POVM, operator positive operator valued measurement, on all her probes as a single quantum system. Okay, and she can derive more information compared to the individual attack, and that's why this is very powerful attack. And This also enables her to take advantage of the correlations in a better fashion than in the earlier incoherent attack. Then the third one is the coherent attack. It is the most powerful attack. It's the most general and most powerful. And here the Eve treats the entire transmission, as you can see here, as one system. So she uses a huge dimensional probe, and she treats the entire thing as one system, and she will entangle her system with a probe of huge dimensionality, with Alice's transmitted photons, and she will have a huge dimension quantum memory and a huge dimension quantum computer to execute such an attack. Okay, so it is very, very difficult, extremely difficult, to establish security proofs against such an attack. Okay, and also, having said that, it doesn't appear that this kind of an attack is possible in near future. But the beauty of quantum key distribution is that it still considers such systems, such possibilities of potential quantum attack in near future, and to safeguard the present system. And I think with that, I come to an end. And thanks to my team. These are my team members, and I'll be happy to take questions.
Yes, ma'am. I think there are a few questions. Akshat, can you read?
Yeah. So yes.
Yeah. Should I dictate? Can you go
No,
back?
I think I'm reading. Yeah, yeah.
Okay.
So one
Okay.
question is clarify the classical channel and the quantum channel. So the classical channel is again the optical channel. It can be an optical channel. It can be IP network. It can be anything which is a broadcast. It's not very specific. But a quantum channel is specific, because here I'm sending the quantum entities. It's now basically it's of two categories. Either it's free space, or it's fiber based. In satellite QKD, it is free space. In aerial platform, it is free space. In terrestrial network, it is fiber based. So these are the two networks. We usually work in 1550 nanometer wavelength range, standard telecom wavelength. Coherent attacks are mostly theoretical in nature, sir. Because these are mostly, prescribed, and some mathematical formulation of these attacks are there. But I would say any implementation, whether on simulation basis or on practical basis, have been done mostly on the incoherent attack, which is the individual attack, like beam split. A lot of attacks are being explored using beam splitter. It's a very important gadget for attacking any um, for attacking any or to devise any attack for a QKD. Okay. Thank you, ma'am. And yes.
Okay, I think all questions you have solved, right? Already answered. The for the participant, the PP, the all the material will be uploaded in the classroom. Yes.
Yeah, I'll be sending my slide right away.
Yes. There is one more question. I think you already answered, right?
Impression, no, I didn't get this question. Eavesdropping attack, reply attack, I don't know. Impersonation attacks, impersonation attack, data tampering and modification, yes. Denial of service, it's a very, it's a very important attack. Like this attack, can I verify on simulation? Yes, you can. Particularly data tampering, denial of service, those attacks can be done. Yes. What is the length of secret key in current state of art? Yeah, I just mentioned. I mean, if you consider CVQKD, it is around megabits. If you consider discrete variable QKD, like BB84, BB84 with Poisson distribution or weak coherent stores is very less distance, but say BB84 with single photons can go till 100 kilometers. See, because when I'm saying kilometer, no, when I'm saying distance, no, you have to understand it is limited by the detector's efficiency. It is also limited by the attenuation of the channel. Okay, so around say 100 to 110 kilometer for fiber QKD, and range is in kilobits per second. So I answered this question: that why does it depend upon the distance? Yeah, it does depend upon distance, attenuation, then ambience, and the protocol.
Okay. Thank you, ma'am. It is very wonderful talk. We also enjoy as an organizer. I am also learning from you. Thank you
Thank
very
you,
much,
ma'am.
ma'am.
Thank you.
Yeah, thank you, participants. So all the material will be uploaded on the classroom. Kindly check your classroom canvas. Sorry, and thank you very much, ma'am. We are closing the session. Bye bye.
Thank you, ma'am.
Bye bye.
Bye.